Okay, everyone, we're going to go ahead and get started. My name is Sam, and I know many of you, and hopefully you guys know me. I'm a health services research analyst at the Data and Research Center, part of the All of Us research program. So welcome to office hours today. Before we introduce our speaker, Aymone, I'm going to give a few announcements that may be useful for you and your institutions. So the first announcement I want to make is JAMIA, or the Journal of American Medical Informatics Association, is seeking papers and manuscript submissions for the focus issue of the All of Us research focus issue, which is looking at the All of Us research program, return of value to communities. So if you scan the QR code, you can get more information about the topic requirements and the deadline. So I'll give everyone a few moments to scan the QR code. Our next announcement is Baylor College of Medicine, All of Us Evenings with Genetics program is offering a 6-week Train the Trainer session starting in February. And these sessions highlight the All of Us Researcher Workbench to include how to create a data set, working with phenotypic data and genomic data as well. So scan the QR code if you would like to register for the Train the Trainer sessions. And those will be hosted in February on Fridays from 2 to 4 p.m. Central Time. And our final announcement today is about Love Data Week. So the Love Data Week is a webinar series that's hosted by the National Library of Medicine and is providing insight into the researcher workbench and the role of the library. So this Love Data Week will have various webinars, and this one that we're highlighting here is just focusing specifically on the All of Us researcher workbench. So if you're interested in joining that webinar on February 13th, please scan the QR code. It will be hosted from 3 to 4 p.m. Eastern Time. I want to note that that webinar will be offering one continuing education credit from the Medical Library Association and is approved for data services specialization. So if you're interested or need that credit, feel free to join. Okay, I also wanted to announce, if you missed it, in case you missed our last Friday office hours, we have posted it on the User Support Hub. The video and the slide deck are available. I do want to note that actually would be a great introduction to OMOP and EHR structure, which will help you understand more about what Aymone is going to go over in her session today. So if you have time later, scan the QR code to kind of access that video and learn more about the All of Us EHR data structure. I do want to have a disclaimer before we begin today. So the presentation today is intended to show a little bit more about data wrangling in this researcher workbench, and we're going to specifically look at specific tables and SQL queries. We have participant privacy at the utmost importance here at the All of Us research program. So any participant data and associated information during this presentation is aggregated summary data in compliance with our data and statistics dissemination policy. The data shown is solely for education and training purposes. And so if you're trying to replicate any information in the workbench, some counts and statistics may vary. You can learn more about the All of Us research program policies on our user support hub. And I will link that in just a moment. So I'm going to introduce Aymone, who is our speaker today. A few of you guys have noticed she's done several office hours, and they've always been incredibly insightful. So Aymone is a data scientist here at Vanderbilt University Medical Center, and she works with the Data and Research Center. She leads data science and engineering efforts for the digital health technologies, our Fitbit information. She's involved in the back-end and front-end processes of our curated data repository and works closely with the curation and research support team. She discovered her passion for data science after working a few years studying business and accounting. She holds a master's degree of science in data analytics and information systems, accounting, and business management. And before working at Vanderbilt, she worked as a data science team member for a cybersecurity company. Aymone is incredibly well-versed with the All of Us data structure, and we're very excited to have her speak to you all today. So with that, I will move on to the next slide. Aymone, would you like me to advance your slides, or would you like to do it on your own? Okay. Wait, did you say you could do it? I think I read your lips. Okay.
Yeah, sorry, I was muted. Yes, I can do it.
Perfect. Oh, before we start, I just want to say if you guys could please hold your questions till the end, and you're more than welcome to put them in the chat, and myself or one of my colleagues from the DRC will answer along the way. And then any that I feel like are great for Aymone to answer live, I'll put those at the end of our session today, if that's okay with you, Aymone.
Yes.
Okay.
Sorry. All right, so I will now share my screen. I hope everyone can see this. Welcome, everyone, and thank you for being here. Hope you're having a good day. And today's Friday, so the weekend is here. So today's presentation will focus on two main things. In the first section, I will give a explanation of the OMOP hierarchy and how to use it in SQL to collect data. And then in the second session, if we have time, I hope we will, I will show you how you can use BigQuery sessions for more efficient queries. Now, how is this going to benefit you? I think all of you will benefit from this presentation because understanding the way that the OMOP hierarchy works will help you be a better user, even if you just use a cohort builder and a dataset builder. Because, for example, if you know what is the parent concept ID for a condition that you're looking for, you can just click on that and click on that one concept ID and get everybody that falls under that instead of clicking on multiple concept IDs at the same time. And then if you're using SQL, you're learning it and writing your own queries, of course, it's going to help you write more efficient queries and correct queries to actually get everybody that falls within the criteria that you need. So overall, like it will help you be a better user of the data, even as you rank all your data, it will help you better understand why the rows are the way that they are. And then the second session, though, that's for people who are a little more familiar with SQL, but everyone can benefit from it. So if you're trying to find ways to make your queries more efficient, BigQuery session is a really cool tool, and I will show you how to use that. And some notes will focus only on EHR data today. And as Sam mentioned, we will show aggregated counts. And before vocabulary tables like concept tables, those are publicly available and they don't contain any participant information at all. We can show real data for those. Okay, so let's get started with the OMOP hierarchy with a quick review of, what is a concept in OMOP. So a concept is the basic unit for in the OMOP ecosystem. So a concept is every code coming from any vocabulary. And the concept ID is a unique ID that is associated with each of these concept codes. And you can find information about the relationship between the concepts through the concept relationship table and the concept ancestor. Those are the two tables that I will focus on later to explain the hierarchy. But in the concept table, this is the basic information that you have for a concept. So you have the standard concept ID, that is the official concept ID that has met all the quality control requirements that we recommend and OMOP recommends using in your queries. And then the concept name is the English description of that concept. Then you have the domain ID, and then the vocabulary. You also have the class in the vocabulary. And then you have a column, standard concept, telling you whether it's a standard concept or not. And then concept code is the source code, the code in the source data. And the valid start date and end date give you the interval within which the concept is valid. So if you see anything 2099, that means as of now it's indefinitely valid. And then if it's valid, the invalid reason field will be null. Now, if it's not valid, of course, the date will show the date, the time where the concept became invalid. And if it's not valid, it's either going to be because it's deleted for some reason, or it's been updated. And if it's been updated, if it's been deleted, you will not see the concept ID in most of the OMOP tables anymore. If it's updated, you will see the replacement ID, and the way to see the ID that has been used to replace an updated concept ID is to use the concept relationship table. So that's a nice transition to that one. So the concept relationship table is one of the two tables that helps you to see the relationship between concepts, because in the OMOP system, all the concepts are related by some sort of hierarchy, right? So basically answers the question, how does concept ID 1 relate to concept ID 2? And there are over 500 unique relationships between concepts. That's a lot. So you can see with the example here, I was talking earlier about a concept being updated. So here tells you that concept ID 1 has been replaced by concept ID 2 as of 2012. So because there's so many unique relationships today, we'll focus on just a few, some of the most important ones that you will most likely come across. So we'll focus on the maps to, is a, and subsumed relationships. So maps to, so if you see concept ID maps to concept ID 2, it simply means that concept ID 2 is a standard concept ID. So the official OMOP concept for the non-standard concept ID 1. So you can go about this multiple ways. If you have the non-standard concept, don't worry too much about the SQL here. As we see later, you should only need to use concepts ancestors most of the time, but I just wanted to show you some of the code here. So concept ID 1, you want to find the standard concept ID for this. You just plug it in the word clause, and then the concept ID 2 will be your standard concept, and you need to add the end relationship ID equals maps 2. And then in here, let's say you have the source code, you don't have the non-standard concept ID, you just have the source code, and you want to find the standard concept ID for that. As you saw earlier, the concept code is what contains the source code. So you need to go through the concept table and then join that with a concept relationship so that you can get to the standard concept for the source code. And those are the standard concepts for those concept codes. And then there's the map from, which is basically the reverse. So map from, if you have concept ID mapped from concept ID 2, it just tells you that concept ID 1 is the standard concept for concept ID 2. Now, the other relationship is concept ID 1 is a concept ID 2. As the name implies, it means that concept ID 2 is the ancestor concept ID of concept ID 1. So here we're trying to find the ancestor of breast cancer. And we're looking at Athena, and we know that the standard concept ID for neoplasm of breast is 81251. So we plug that in as concept ID 1. And here we don't really need a join. I just wanted to see the English name for the ancestor. As we saw, the English name is in the concept name column from the concept table. So we just join that, and then concept ID 1. So concept ID 2 is the ancestor concept ID. So we see that neoplasm of breast in the HOMO hierarchy has 3 parents. The next one is subsumed. So that's the opposite. We're trying to find the descendants of neoplasm of breast, which is what most researchers want. They want all of the descendants of a particular condition or particular drug or procedure. So you just plug the concept ID 1 here, and your relationship equals subsume, and then you will find all the descendants. This is just the first 10 rows. There are way more descendants for neoplasms of breast. Now, in Athena, this is a visual representation of what we just saw in the SQL. So you got neoplasm of breast, the 3 parents here, and then all the descendants. Now, like I mentioned earlier, concept ancestor is the table that I will mostly focus on because that is what we recommend. The concept relationship table contains only the direct parent-child relationship, but the concept ancestor table provides the complete hierarchical relationship between concepts. So it is a combination of the concept table, the concept relationship table, and the relationship tables. So you got grandparents, grandchild relationships, parent-child relationships, all kinds of relationships are in that table. And it's meant to make it easier for you to query all of the descendants or all the parents, if that's what you want, of a particular concept. Now, here we're trying to find all the descendants of neoplasm of breast again. So all we have to do is to put neoplasm of breast concept ID in the ancestor concept ID column, and we can join that with the concept ancestor. And again, here I did not need this. This was optional, was so that I could see the string names. And then we get all of the descendants here, descendant IDs, and then this is the parent. So you may have noticed these two columns, minimum levels of separation and maximum level of separation. Most of the time, you should not need to use it, but I've seen use cases for it. Most people use the max level of separation. You can do pretty much everything you need with that. So what it is tells you, as the name implies, how many levels there is between the concept that you enter and the different children or the different parents. I will show you a visual, like what that looks like visually. But basically, if you have max level of separation 0, it means it's the concept itself. And then maximum level of separation is 1, is the next closest level, and so on and so forth. Let's see this example. This is a very simplified version of atrial fibrillation concept ID 313217. So if we're looking for all the descendants of atrial fibrillation, this will have max level separation equals 0. That means itself. And then the very next descendants will have level of separation is 1. So, and then let's say I clicked on one of the descendants, I click on persistent atrial fibrillation. It will give me, the descendant of this guy is long-standing persistent atrial fibrillation. That's level 2. So the further down you go, the higher the numbers go. So this is how it looks like in its SQL. So if you query atrial fibrillation from the concept ancestor, and you see all the descendants, again, there's a lot more than the graph showed, but you can see level 0 itself, level 1 are the ones from this line, and then level 2 is the descendant of one of the descendants. So this is helpful if you have a specific concept ID or multiple concept IDs and you want to find the children, you don't even need to worry about this field. But I've seen cases where researchers want to find every condition that a group of participants can possibly have. So in that case, you may not want to query every single row related to every single parent and concept. So you may want to limit yourself to maybe the top conditions. So level 1 and level 2 for the people in your cohort. So that will make sure that your query runs, because if you try to query the entire condition occurrence table, for example, even if you limit it to a set of participants, your notebook might crash. But if you limit it with just the top levels condition, then you will get the most of the data that you want. Okay, so let's try the opposite. So ancestors, those are the ancestors of atrial fibrillation. Again, the number goes up the further you go up. So max level of separation equals 0 itself. The very next level, so the direct parent is 1. The parent of a parent is 2. And this is what that looks like in the SQL query. And the table returns 0 itself. 1 is a 2 that we just saw, 2, and so on and so forth. And you can go way up to like disease. At this point, it doesn't really mean anything. So you need to play around and figure out which level you want to stop at. Okay, now something that I want you to understand about the descendant-parent relationships, having a visual example will be helpful. So all people that have, let's say, persistent atrial fibrillation will be classified as having atrial fibrillation, right? That makes sense. But not all people who have atrial fibrillation have, let's say, persistent atrial fibrillation. They may have controlled atrial fibrillation and not any of these. They need to have at least one to be classified under it, but they don't need to have all of them. So this is something you need to keep in mind when you're trying to figure out which level of separation you want to keep, or which concept ID you want to use. Okay, so now let's look at some practical queries for the main EHR domain. Some of the things that some of you might need to know, want to know, and especially look at the difference when you ignore the concept ancestor table and just go straight to the condition occurrence. So for this example, we're trying to find, everybody that has neoplastic disease. So benign, anything. So we found in the Athena that this is the concept ID for neoplastic disease. So we enter it as the ancestor, and then we get 13,000. But if we just use the condition occurrence and the condition concept ID, we get 300. So the difference is dramatic, especially for condition. I would say 100% of the time, use condition concept ancestor. And when you're using the click and point tools, it's doing that in the background. It's using the concept ancestor and the concept relationship sometimes. And you might not see it because it's deriving it from derived tables, but it's doing this exact same query in the background for you. And then you can still get the same count. If you have the source codes, you don't have the standard concept ID, you can still go through the concept table, enter in the concept code column, and then join that to the concept ancestor, join that to the condition occurrence, and you can still get the same numbers. Now, for some other domains, the difference might not be that dramatic. Like you will see for measurement, sometimes using the concept ancestor doesn't really make a difference. But still, if you're not sure, just use it. So here, an example, we want to see everybody who had surgery. So that's a procedure. So it's the same query, except you replace the table based on which domain that you're in. So we want procedure, so we just join it with the concept ancestor. And since we have the code, we're going to go through the concept code to merge, and then we get about 18,500 people. But if we didn't do that, if we just use even the procedure occurrence and concept table, we will get 5,000. The difference is drastic. For drug, same thing. You merge the main table with a concept ancestor, and then you get the counts. If you don't, you get it's a little less dramatic, but it's still a big difference. For visits, I'm trying to find all inpatient visits, and let's say I just want to do this with the visit occurrence table. I guess I get about 103,000, but if I use the concept ancestor, I'm getting 107,000. Now, measurements, like I mentioned earlier, sometimes if you get the very top parent concept ID, whether you use a concept ancestor or not doesn't make a difference. But sometimes it does. So I would say if you're not sure, just use a concept ancestor. Here, for example, if you don't use the concept ancestor, you'll think there's nobody with this lab measurement. But if you do, you can see that there is. Okay, that was it, and I will take question for that at the end. Before we move on, before that, I wanted to talk briefly about the BigQuery session. So we had a little questions about the possibility of creating temporary tables and using them interactively. And yes, you can do that with BigQuery sessions. If you're a SQL user, you're trying to find ways to write efficient queries that can run fast and not use so much of resources, this is a good option to look at. I think Sam will put in a link for you that you can learn more about that on BigQuery's page itself. But what is a session is basically an environment that you create in your notebook, and then it captures all your SQL activities, right? So temporary tables, temporary function, and variable that you create there can be used throughout the session interactively and build on one another. You can have multiple sessions active at the same time, and you can have the history of each section saved. So it does maintain transient data, which is what makes it possible for you to use your variables and temporary tables throughout. And then there's no additional cost that if you were just using a regular SQL query in your notebook. Now, there are limitations, but frankly, I think I haven't encountered any of this, and there's a way to go around it. So every query is run in the location where the session was created, pretty easy. I mean, if the location of your database is USA, that's where you run the query. And then the session, if you're not using your session, it will be automatically terminated within 24 hours. But the session lasts 7 days. So after 7 days, all your variables and temporary tables will not be there. But if you save them to the bucket, then they're there permanently, even if your session ended. And then here you've got the maximum size of the variables. To put it in perspective, so you said a session you can use about 10 megabytes. The person table, the whole person table has about, I think, 70 megabytes. And you're not gonna query an entire table. We don't recommend doing that at once. So you create specific columns, you have conditions in your work clause. So you can do a lot of things in one session. And remember, you can have multiple sessions open at once. And you can save those in your bucket and go back and add more to your code. So this is not, it hasn't really been a limitation for me. And no concurrent queries are allowed. So that's easy. Just wait until one query is done and to run the next one. So I will show you briefly what the actual code looks like how you can implement it. Give me a second to stop sharing this and share the other notebook. I hope everyone can see that. Yes, I think that's the right screen. So this is how, there is a way to do this in R. I just haven't tested it yet. If anyone is interested to do this in R, you can send us a help desk ticket, and we can figure it out together. But the first thing that you need to do for a BigQuery session after you have set up your libraries and environment variables is to create a session. And this is literally the code to create a session. You can just copy paste it. All of this code can be basically copy pasted. Now here you can choose to create initial temporary tables with your session creation. So here I'm creating 2 temporary tables, one from the activity summary, which is a Fitbit data set, and then one other Fitbit data set with personality, heart rate value, daytime, which is, as you know, the Fitbit data is very large. So this is part of the use of sessions that you can query large data set in small chunks, smaller chunks, and then join them together. So I created these 2 tables, temp 1 and temp 2. It took only 27 seconds. Now, the second thing is to grab your session ID. This is your token or the fingerprint of your session so that BigQuery knows that this is where basically all your variables live, like the temp 1 and 2 are there. And then the next one, it's simple code, but I put it in function so I can use it without having to write this every time. Again, can be just copy pasted. I basically feed in the session ID and this is code to write in your queries, and this is code to query in session. So let's test it. Here, I'm creating another temp table, which is a merge of the 2 initial temp tables that I created. See, you can so temp 1 and temp 2 just exist within the session, and I can do whatever I want with them as if I had like my own database in that session. And I create temp 4 based on temp 1 and temp 2, and it took only 11 seconds. Now, I'm creating another table, team 5, where I'm joining with the person table from AOU. So you can also join the team tables with other tables within the AOU system. And that took only 5 seconds. And then now I'm just gonna try and query my team tables. How many people do I have in team 5? Or how many people in team 5 have conditions as well? I do that by joining the condition occurrence table. You can even and so you can write this is a very simple query, but you can write more complex queries, split them into multiple ones for efficiency, and then join all the teams together. And because it stays when I'm writing the query here, like it's a temporary table, it's not outputting anything. It costs less than if I try to run this, get a data frame, and then running that data frame and merge them together in Python. Like it would cost a lot more than if I just did all of that in SQL and merge the teams together in one or multiple steps. And then you can even import external data and then join that with your team table. So here I create a fake data with fake person IDs. You can use this kind of code to load it into the environment. And this is not specific to BigQuery sessions. You can actually do this with any CSV file. I think we have a code for this in one of our featured workspaces. But so I'm importing the example.csv and I'm loading it as an external table. And then I can just join it with my temp 5 table that I created earlier and do whatever I want with it. Now, again, you can save any of these data frames to your bucket and it stays there permanently even after your session is ended. You can have multiple sessions at once in the same notebook, so you can do a lot of things. So this is just one way to do it. I'm sure there are other more creative ways to do it. Feel free to look at the link that I put there and just play around with it. That is the end of the presentation. Yeah, we're now open for any question.